Thanks for starting to work through some stuff in lab. A lot of people are getting to some advanced Git usage. For the purpose of this week's exercises, all you need to know how to do is commit, add, push, and pull. So you don't need branches, but I wanted to point you to some exercises where you can explore that because it will be something that you might find useful in your final projects, and if not, certainly something that you will find useful if you work in software engineering for any company as an intern or whatever else. Not a lot of scientists use branches. So that's even an advanced feature of Git that many different people don't use. What's up?
Do you apply it in your life?
Pardon?
Do you apply everything you're teaching?
Everything I'm teaching, I do apply in my life. In my science, and I also do a lot of different programs outside of my science. So I've developed a number of iPhone applications and Android applications and web applications. And in all of that, I've used Git a lot. I've used Python a lot. I've used other programming languages as well. But my original programming class was taught just like this one, using a particular language. And the concepts, once you learn how to do things, how to think, it's something that if you want to, for example, make a phone app for whatever reason, that you'll have the skills to try to do that, to be able to do your own research and to approach that the right way. So yeah, everything I'm teaching are things that I use in my almost daily life. And then as well, it's not just, I use even more things in my daily life, if that makes any sense. But I've kind of picked the things that I think will help you, whether you want to use coding for projects, whether you end up working with a colleague who's a programmer and you're not a programmer yourself, whether you end up managing programmers, and enough skills that could get you an internship. Because even if you want to do something else, you might find at some point that you need some money, maybe to pay for school or whatever, and these skills are so marketable. So a lot of colleges offer like work-study jobs, but those are more like you work in a cafeteria, or you do cleaning, or you work in a library. This is the kind of stuff where you can get paid and learn at the same time. So even if you do something else, if you master the concepts in the first 3 chapters, and certainly if you master the concepts in all 4 chapters, it's something that you could get a job doing, no matter if you decide to study that in college or not, just because it's so useful. Very good question, Crystal. Okay, so in the next section, and this will also go into the next section of the exercises, you've seen exceptions in your Python career so far. They're exceptions. You've seen things like type error, IO error. Basically, when you're trying to run something from Python or the IPython console, sometimes it'll print an error or an exception. Exceptions, so far, how we've seen it, are when your code crashes. You can also create your own exception by creating a subclass of the class exception. Using your own exceptions will help you be descriptive in what type of error the code is creating and why you as a programmer decided the best way to handle that was to use or throw an exception. So one time where you might want to use exceptions is if, say your code is relying on the user giving it a file. The user points your code to a file, and then the file isn't there. You don't want your code to keep running, because what's the point of that? You want it to somehow say that this is a problem. So one way to do that would be to raise an exception, and to have whoever's using your code deal with that exception however they want. One person might decide when there's that exception to display a big pop-up in giant red bubbles saying, upload a file. Another person using your code might decide to display a smiley face and a unicorn and say, hey, there's a problem. What raising an exception does is it alerts everyone there's a problem, and if you don't do something about that problem, you can't move on, essentially. But you're also able to, in Python, decide to, if I get this sort of exception, I should do this, I should do that, I should do that. So you can use exceptions in a way that it doesn't always crash your code. And we'll learn that in a bit, and it's called the try except block. There's also a concept of assertion. Assertions are items in your code checking items which should be true if the users, which can include you, of your code have followed the instructions specified by the documentation of your functions, methods, classes, and codes. Assertions check things that should never, ever, ever happen. So someone can always try to upload a file that maybe it's the wrong type of file. That's something that could conceivably happen. Assertions are more used for if you write your code and it should take in an integer, and someone gives you a string instead. That isn't a user in terms of like someone who doesn't know how to program. It's an actual programmer who should have read your code and seen that it should take in an integer. So programmers don't always follow instructions, and moreover, programmers make mistakes. So you can use assertions in your code to double check that the instructions are being followed and to crash the program if they aren't. So usually when a code is running for the public to use, like on a website, assertions are not enabled. Assertions are more by programmers for other programmers. And if you put in a lot of assertions, it can help you make sure that your code is working right, that you're not doing something incorrect. But it's more for programmers themselves. Whereas exceptions can be things that, you know, maybe it's too hot out, so you want to throw an exception and say, well, my temperature sensor can't work in this situation. There are things which can potentially change. Like based on the weather, sometimes the code shouldn't work. And assertions are things where it's literally, it should never happen, but you as a developer want to double check, help yourself double check that everything is working as you think it can. If you build assertions into your code, you can always run the Python code in a manner where the assertions aren't executed. In this way, you can use your assertions while you're actively working on the code as a safeguard, and when you run the code for its design purpose, disable them. And the reason why people often do this is that when the code is in its final form, the assertion might sometimes take a while to actually check. For example, maybe your code relies on getting a string or a list or a NumPy array where every element should be an int. And you could have an assertion that actually checks that. It's in the documentation. But if you did this when the code was actually running, you know already as a programmer that you've kind of checked all the different cases, and you don't want to delay returning by checking through every item in a long array when a user is waiting to, say, download a file or something like that. It would be a waste of time. So again, assertions versus exceptions. Because assertions can be disabled in the final code, it is important not to use assertions for logic about errors that could actually happen and should be handled well. Basically, assertions will always crash your code. Exceptions are for things that could conceivably happen. They're not really desired, but they could potentially happen. Assertions are used for things that should never, ever happen. What's up?
Let's say someone manages to break your code, right?
Yeah.
Can there be like a backup plan after that?
Yeah. So we'll learn about that in a few slides. It's called try, except, and finally. So that would be, for example, if there's an exception, you could say, try this. If it breaks, do this. And then no matter what, whether it breaks or not, always do this. And you can write that into your code. But as well, in terms of when we write our code, and this is also another profession, there's a profession which we heard a little bit about from Andrew Pryor-Miller called quality assurance. And what they try to do is if you write a lot of code, and I'm the quality assurance person, I try to break your code. You write your code, and I try to say, how could I possibly make this crash? How could I possibly do something to break it? And that makes the code better, because sometimes when you try to test your own code, you think everything works, but really someone who has an external perspective can really test it. So that's an entire profession. You can do that professionally. And that involves a little bit less programming than this. Oftentimes, so far, it's been, sometimes it's as much as clicking. So you could have, you could write an iPhone app, and then I could look, and I could try to push all the buttons and all the different combinations, and then I could be like, hey, if I push this red button after this blue button, this happens. It doesn't work right.
So when we have our final project, will you try to do that?
That's a good idea. So definitely we're going to want to do what's called testing. So, no, don't worry. All of these strategies are you as a developer. You want to try to make your code as strong as possible. So I don't think we'll have someone external doing this, but putting a lot of assertions in your code, trying to make sure to try all the different possibilities. You could even have another person on your team, once you put together the code, try to figure out ways in which it could break. And sometimes codes don't work for every situation. If you know that something will break sometimes, that's also okay, but it's better to know about it than not know about it. Because then if someone's like, it doesn't work, you can be like, well, we know about that, we're working on fixing it, instead of, I had no idea, I thought my code was perfect. So it's always good to know about it, even if you don't have enough time to fix it. Another entire profession, people work in a field called computer security, where they try to figure out ways of breaking code that involved, like when we SSH, you see how we can get into another machine. If that other machine had code that wasn't really working well, I could, even without you giving me the keys, the password, I could potentially get into that other machine. And so a whole profession is trying to figure out ways to prevent that from happening, because if I could get into a machine that Google owns, then I could change google.com to christine.com and make a lot of money, and they wouldn't like that. And this happens all the time. And it's a fun profession. There's also a portion of that profession called penetration testing, which is essentially trying to get through boundaries or walls in an organization. I'll get to you in a second, Nico. And for those, sometimes that involves what's called social engineering, which is basically things that aren't computer related, but still security flaws. So for example, I could call up the secretary or administrator assistant at Google and say, hi, I am Eric Schmidt, CEO of Google, and I just was wondering the password. And if he gave me the password, then I could go ahead and use it. So that didn't involve any computer hacking. It's totally illegal. But it's a way of getting into remote computers. So some people are paid, like Google might pay a whole team of people to try to break in. And it's similar to if a bank paid bank robbers to try to rob the bank to see how secure the bank was. So you can get paid to basically try to figure things out.
Someone actually, Google forgot to register their domain once, and then someone bought Google's domain, and they ended up earning like ridiculous amounts of money.
Yeah. So that's an example, not necessarily of computer hacking, but of ways in which sometimes these flaws aren't necessarily computer code. They're just, people doing the wrong thing or people dropping the ball on tasks that they should do. So yeah, penetration testers sometimes don't even use much computer code. They're more like running tools and trying tests. So let's look at how we actually do an assertion. All you have to do is write in your code assert and then some Boolean expression. And if that expression is not true when the Python code is run, it produces an assertion error exception. This can be handled in a try except block, just like any other exception. We'll meet the try except block very soon. If they aren't handled, it will crash the program. Assertions can also be followed by optional arguments, which will be given to the assertion error and are by default printed at the time of failure. So programmers often use these to help them print information about what went wrong so that it is easy to debug. And the arguments are separated by a comma. So this will probably be a little more clear when I give these examples. So here, if I have some variable x and say it's set to 6, I could have an assert statement that says assert x is greater than or equal to 5. I could do the same assert statement doing, let's see, there's a typo in this. There's an extra quotation in the third one. But so you can then input some information about the things. You can even use x as an argument at the time the assertion is set off. You can also turn off assertions by putting a -o at Python when you run it. And you can also turn them all off all the time by setting the environment variable Python optimized to true, in the same way that we set the Python path and path environment variables. So it's a good idea if you're using assertions to double check that they're running. So if you add a line assert false, what's going to happen if I have assert false in my code. Nico?
It'll always return false, so
that'll always crash, and it'll say, great, assertions are running, and then crash your code. So normally you don't assert false. You might more, if you have complicated logic and your function is a little relying upon it being used in one particular way, even if you've documented that, you might want to add in some assertions to make sure. And this can also be a way of debugging. Say you're trying to debug why your function isn't working. Think about all the ways what would have to be true for it to work. Put in a bunch of asserts, and then run it, and it'll see where your logic broke down, and that'll help you debug. And so that's one of the reasons why we're teaching asserts here is now if you have a function that isn't working the way that you expect, one way that you can debug is by literally coding in what you expect with these assert statements. And then when you reach the assert that's not true, then you can figure out why that's not true. Maybe that's a bug in your head, maybe it's a bug in the code. And you can fix either of this. So I've talked a little bit about throwing and catching exceptions. What does that mean? So sometimes the code will throw or raise an exception. These are kind of synonymous terms that is expected or that a programmer might want to take additional action about prior to crashing the program. So you might want to not crash the program if it's expected, or maybe take some action before crashing the program. Python has a way to handle this, and this is called the try except block. And we'll learn about that here. So the syntax is try, some block of code, except, some block of code. And basically, if there's any crashes in the code block, it'll immediately jump to the except block. And then you can do whatever you want. You can crash, you can print a line, you can ignore it. It's up to you as the programmer to decide what to do. This can also be useful in debugging. If you have a crash, you could try something and then accept something and kind of skip over some code and figure out what exactly is happening. So definitely something that's often used by programmers. It's good programming practice and will potentially save you a lot of headaches tracking down bugs to specify which kind of exceptions you want to handle given the class and which you do not. This is critical in cases in which you might decide for whatever reason to totally ignore one class of exceptions. If you ignored any exception in the universe, it might create bugs because you do want to know if your code isn't functioning as expected. So here, for example, if I want to see that my assertions are working, I could try assert false, and if assertions are enabled, then that's always going to have an exception, and then I'll accept assertion errors, and then print, we expected this, just testing assertions here and moving on with our life. Did you have a question, Sierra? And we'll get to practice all this in the labs. Nico, you're going to have to wake up. I'm sorry. If you need to, you can stand up. So I've heard that helps. Yeah. But really, I understand that it is a long day and people do get tired. So if you need to stand up, you can just stand in the corner. And if you fall asleep standing, I'm definitely impressed. Exceptions can be used in your own code in situations where an assertion would be inappropriate because you expect the code to occasionally reach the error state. And you can raise exception with the raise keyword followed by instantiating an instance of an error class. So here I could, in my own code, say raise assertion error and then give it a little string of what to print. And then when the interpreter reached that line, then it would crash and display assertion error. The assert really didn't work. So you can use assertions and exceptions together. And this is one instance where I could also raise a type error, for example. There are a variety of different error classes, and you can make your own error classes. You can also catch multiple exceptions in the same try except block. And you can use, with this as keyword, E will be set to whatever the exception is, so then you can print it or do something else with it. So here, I raise a value error, then I accept either assertion errors or value errors, and then I can print those, and then I would accept a name error, and I could say this, and then any other type of error would completely crash the code. So most of the time your try blocks won't necessarily have exceptions in them. Here I've just given examples with exceptions so that we can see what happens when you have exceptions. Finally, and then we'll move on from exceptions, this will all be things from now on, when your code doesn't work, I'll suggest some of these as debugging strategies. So that's why I'm introducing them. You don't have to memorize them, but I'll be like, why don't you try an assertion? And if I can spot, or if a TA can spot the error, instead of telling you exactly what it is, they can kind of teach you how you might find it yourself, instead of pointing it right there. So now you will have heard this verbally in the textbook, and we'll do an exercise on it. But we'll use it in your other code. When you run into an error, I'll say, well, why don't you try a try except? Why don't you try an assertion? Why don't you assert this and see what happens? So that's why we're learning about it. So the last thing is the finally block. The code in the finally code block is always, always executed no matter what the exception is, or even if there is no exception at all. So here, no matter what, if there's no exception, doesn't matter, we're always going to print, we always reach this code. And that's what the finally block is used for. Software engineers regularly test their code extensively, especially if you're working for a company like Google, where if there's a mistake, it's going to cost billions of dollars. But they do understand that people make mistakes, and their programmers make mistakes. So there are teams to work together to try to make sure that you don't make mistakes. And another great thing is when you write in a lot of these tests, you can try something, and if all the tests work, you can be kind of confident that you didn't royally screw things up. So often they write functions specifically designed to test other functions and assert that their behavior is correct and as expected. I'm not going to go over the testing frameworks, but I'm just going to mention them. So at some point with larger projects, you might want to check out the doc test or unit test modules built into Python. Software engineers take testing really seriously, and it's often a core approach to how they design software, particularly in teams. So sometimes, instead of doing a whole notebook problem or a whole problem or a whole kind of feature, software engineers will write all the tests first before they even do anything. If this works, what are all the tests called? What are all the methods called? What are all the functions called? If this function returns the right thing, write all the asserts, and then finally they develop the function. And then once they develop the function and the tests all pass, then they're good to go. Studying testing strategies and where and when to incorporate them in software development is a chapter on its own. There are whole books about this. So it is something that lets you work on particularly really large pieces of software. You as a new developer might be able to make a contribution, and a very advanced developer will be able to trust your contribution because they have a huge amount of tests written. And they know that even if your contribution accidentally broke things, they would discover it right away. Otherwise, it would be very hard if the code base is hundreds of thousands of lines and you made a small contribution for them to say OK to that. Because they'd be like, well, we really have to understand exactly what you did. We don't trust you. OK, so that's moving on from testing. And again, we'll have one exercise on that this week. But as well, it'll be a strategy that you'll have in your toolbox to help you figure out what's going wrong when you're confused or when something doesn't work. And it's something that absolutely everyone does use. OK, so a couple more. The next section is just a few more endnotes about Python. Yeah?
This past one, could you put a statement after the past one with it right?
That's a good question. So it depends on where the path is. Here, the code, it's not like a break or anything like that, where the code, you can put stuff after the path and it will run. I think, let's try this out in the command line. I think that's the same also if it's in an if statement, but I'll just double check to make sure. So we can actually run something. Python. So we'll do if true, pass print hello, I got here, and then else, print else, never got here. So yeah, so you can pass basically just as a placeholder. Python ignores it. The only reason why you might use pass is otherwise Python will get confused. If you need a code block, you always need a code block. So I can't just leave this blank and do something else. It won't let me. I can't do else print hi. This should cause an error. Yeah. And that just has to do with sometimes even when people say something, it's ambiguous. You know, if I say, aren't you going to the store? And you say no, what does that mean? Are you not going to the store, or are you going to the store? You might have to say, no, I'm not going to the store, or no, I am going to the store, or yes, I'm going to the store, or yes, I'm not going to the store. It's all ambiguous. So ambiguity can happen too, potentially, in a programming language. And if we didn't have this pass, Python would be confused about what to do next. And so the pass is like, I know we should have a code block here, but I don't want any code, so the pass can be used in place of a code block, and it's ignored by Python. So sometimes that can be useful if you want to sketch out definitions of functions. Define, to do later. And I don't know what I'm going to put in there yet, and it's in a big file. I can make a note, pass, and then say, don't forget to fill this in. And then I can use it in another function, and it doesn't matter. I can use to do later, and it's not going to crash or anything. So this can be a way that you can kind of sketch out all the different methods you're going to do, or if one method depends on another, you can put that in without having to, you can still use the function. But you have to make sure to go back and finish it. So it can be kind of a to-do list too. Okay, so when should you use pass? You should definitely think twice before using it. If you find you need to do so for the logic of your code, there's often a better way to structure things. Pass should be rarely required. You can use pass as a placeholder, but that can be dangerous because if you forget to go back and change it, that could cause unexpected behavior. One way to get around this is to mark in some way, either in a comment or by raising an exception, that you should come back to this code to finish fleshing it out at a later stage. But it can also be a way to debug. So if you need, yep?
Let's say you put something in pass, right? Will Python remind you, or do you have to remind yourself?
You have to remind yourself. So Python won't, but if you want Python to remind you, you can instead, these are all great questions, Crystal. So I can instead, something that's like a little bit too better would be, I could raise a to-do exception or something like that.
Does that exist?
This doesn't exist, but I could make it.
How do you define it? How do you define an exception?
So I can do def to do exception, or this would be class, actually, it's a class. So class to do exception, I'm not spelling this right, exception, and then I can inherit from the class exception. And then I'm just going to put a pass here. Okay, let's see if this works now. So def to do later, raise exception, to do later. Let's see if this works. Yeah. So this is another place where you might want to use a pass. Good example. So here, I've subclassed exception. So exception is the superclass, but I don't want to add anything else to it other than that I have like this new name for it. So I don't need to put anything else in the class body. After I finish explaining, I'll take a question from you, Nico. So I've put a pass there, and then instead of putting a pass in my to-do exception, in my to-do later function, I'm now raising a to-do exception. And then you can try and accept to-do exceptions in your code, in your big file, and then when you're finally done, when you're like, I think I've done everything, you can remove that try except block, and then your code will crash if you have any place left with this raise a to-do exception. So that's one example of how you can use subclasses, and this is advanced, but it's something that you can see that it's a little less likely that you'll forget something that way, because you can have the try, except, comma, to do exceptions throughout your whole code, and then at the very end, you remove those, and then if your code still crashes, there's something still to do, because you have a to do exception. You had a question, Nico?
Yeah, what would happen if you just tried to raise an exception that didn't exist?
It will crash and say it doesn't exist. So I can raise a to don't exception, which shouldn't exist. So now to do later, and then it says, I don't know what that is.
So basically it's the same result. I mean, either way, there's an exception.
Yeah, but this time it's a name error, and there could be a ton of other name errors in your code. And here, with this example, we just want to accept the to-do ones, whereas a name error could happen for many other ways. So if you're accepting name errors, you could be missing a lot of other things.
Oh, yeah, you could accept just to do it.
Yeah. So in this case, I could do try. Here, we'll redefine the to-do exception. To make sure this works. So now I could do try. I could try a bunch of code to do later. Then I could only accept to do exception. And then print still stuff to do. And then hopefully this will work. Yeah. So then you can try tons of things in your code, and just, if you have anything to fill out, raise that to-do exception. And then at the very end, when you think you've finished everything, you could remove the try except. And then if you finished everything, then it'll work. And the risk is, if you used a regular exception, you would have tons of other problems in your code that you might not know. Yeah.
Sorry.
No, these are great. Yeah.
I was going to ask, can using too much pass cause you a bug at some point?
Yeah, absolutely. It is definitely, if, for example, you use it for a to-do exception and then you forget about it, it'll kind of help you ignore stuff. It can also cause you a bug in that if you're having to use pass for your if statements, like for it to work, it makes your code hard to read. And you can always rewrite the if statement in a way that you don't need the pass. So it's much better wherever you can to not use the pass. But one example of where you might want to use it is, in this stuff that you might fill out later, for example, or if you just want to debug and Python expects something here, otherwise it's going to be ambiguous for Python, so you give it a pass. Okay, so in the last little section here, and this will be actually all the new material for this week already, so that's good. The last part is a little bit more about Python functions. So far, we've been using functions in a variety of different ways. We've defined them with parameters. There are many more options with functions, and we've actually been working with functions that work like this. But basically, you can define a function in a way that allows certain parameters to be optional, and also, or also give default argument values. There are ways to explicitly require whoever's using the function, the caller of the function, to use a parameter name to give it a value called keywords. There's even a way to specify that a function can have an arbitrary number of parameters or an arbitrary number of keyword parameters. Finally, there are ways to use functions without having to give them names at all.
What?
Yeah, so we'll get to learn about that. So these concepts are all useful in the course of function design, and they're covered in the next few slides. It will probably be the case that mostly for this class, you're just going to be using functions that are like this. And you don't need to define functions like this outside of exercises, but it's good to know that they do exist, and one day when you do more advanced code, it's going to be very, very useful. And you may find in your projects having to use this or work with codes that use this. So the easiest way, the first thing that you can think about, is you could specify a default for a parameter by putting an equal sign and the default value after the parameter. In the following example, the function miles driven, speed miles per hour is given a default 65. So that the miles driven function can be called with either 1 or 2 arguments. So what is this first print going to return? Print miles driven 2. What do you think, Crystal? So when we call it with miles driven 2, what does 2 correspond to? Which parameter is 2? So miles driven isn't a parameter. Miles driven is the function name. What are the parameters of miles driven? What's that, Moa?
2 and 55.
Those are arguments. The parameters have names. What are the parameter names of miles driven? I called you Momo on accident. Sorry. Well.
Hours driven and speed MPH.
Yeah, so those are the parameters. Hours driven, speed MPH. The function name is miles driven. The function argument is 2. So which parameter does 2 correspond to? We have 2 options. Well, hours driven. So hours driven is 2. And then what is the function going to return?
It's going to return 110.
Almost, yeah. 65 times 2 isn't quite 110, but you have the right idea.
Oh, for some reason I read it as 50.
55 is 65. Yeah, it is small. So it's going to return, you didn't give it a speed miles per hour, you just gave it an hours driven, but there's a default for speed miles per hour, so it's going to return hours driven, which is set to 2, times 65. Yeah, and then what about the second one?
65, which is the speed MPH.
So in the second one, what parameter does 2 correspond to? And what parameter does 55 correspond to?
Speed MPH equals 65.
65 is only set to that if you don't give it a value. So in the first one, it's set to 65. In the second one, we give it a value, so it sets it to 55 instead.
So it changed.
Yeah. So what's the second one going to return?
110.
110. So your first answer. So basically that lets you write functions in a way that you don't always have to call them with all the arguments. If there is really a default value, that most of the time it's this way and only sometimes it's something else. So if this was miles driven on the highway, it might make sense. Like most of the time it's 65, but sometimes it's a construction zone, so it's 55. Sometimes you're in another state. Sometimes it goes up to 70 or 75. But most of the time on the highway, it's 65.
Sometimes it's in some streets.
Yep.
What's
up, Nayeli?
You can use default arguments working with numbers, or can you use them like printing with a string, like
Yep.
MH equals I.
That's a good point. You can have it be literally any Python object. And I'll give one caution, which is the next caution. So it can be any Python object. It can be a class. It can be whatever. But here's a caution. Don't use mutable default arguments. Never use something mutable. For example, a list as a default argument. And this is one of the reasons why we learned about tuples. Because each time the function is called, the same mutable object can potentially be modified. So if I have a default argument that's a list, and then I add something to that argument, every time I call the function from now to infinity, it's going to add something to that same list. So if I call the function 500 times and I add 500 things to the default, it's going to be 500 things long. So it's kind of not expected behavior. Most of the time, this is not what you want.
So say you call a function that adds something to the list, to put a list inside it, could you potentially print the list out and have it change?
Yeah. So this is def. Let's try this out. So I'm going to def don't default list equals this. Then I'm going to do So now I'm going to call don't. Oops. Oh, I just misspelled that. Here we go.
What I'm wondering.
So, well, I'll print it too. That's a good point. So I'll print a def list.
But what I was wondering was
whether you can keep talking, I'll listen.
like say you didn't have a kind of default argument.
Yeah.
But return the list every time you call the function.
Oh, then it's a new list. So here you see that I call this don't, and because the default is mutable, every time it's using the same list. So it keeps on adding to the list. So instead, if you wanted to have a default list,
what if you have the list in the argument?
if you have a list in the argument, it makes a copy, so it's different. So it's just with the defaults that it uses. So I can do def don't list. I will call this do instead. Do list, and then I'll do list plus equals 5, return list. So I could do, and then I could give that an empty list, and it's fine.
Now, what if you gave the first one an empty list? You gave don't an empty list.
Yeah. Oh, I see what you mean. Yeah, let's. I think don't giving it an empty list is fine. I think that'll be fine.
Yeah,
So.
and then what happens if you remove that empty list and just call it like usual?
That'll keep on adding it.
So the default arguments are separate from the arguments.
That's right. Yeah. So it's a bit weird. So what you want to do instead, if for some reason you find yourself ever wanting to have a list or something mutable as a default argument, you could do default list, set it equal to none. Then if default list is none, then default list equals empty list. Return default list plus equals 5. Well, let's see. I did something wrong there. Oh, there we go. Default list plus equals 5. 4, return default list. Okay. So now we can call it, and it should always be, if we don't give it an argument, 5. And then if we do, say 5, 4, 6, then it just adds 5 to the end of whatever we give it. But we can also call it like that. So if you ever need something mutable as a list or mutable as a default argument, most of the time you want to set it to be none as the default and then check if it's none and give it a brand new mutable object at that point. And that's, again, advanced usage.
Why are immutable objects, like immutable lists, even existing? Because when I think about, like, say it was an argument, I think, well, if you have a tuple, and this is an object, and not an argument, if it was an object, yeah, that one's going to be modified. So what else can't be modified? That would mean that all of the other default arguments would not be able to be modified, like, say, strings.
Yeah, so a tuple...
But the strings are the same mutable objects in their normal Python, so why are lists exceptions?
So lists versus you mean like if I give a mutable string. The reason why is that string, that's a good question. Because you're right that strings are also, so try another don't. Let's try another don't.
Why don't we need a special string or a special string?
Yeah, let's see how this works. This is all good. So default string plus equals using it again. And then I'm going to go all the way up here, hopefully, and be able to change this to a default string. And I'm going to call that with an empty string. So let's try don't.
Why does the string work like a tuple?
Yeah.
Yet the list not. I mean, because the string is mutable if it's an object, correct?
Yeah, so I think it actually is the case that a string is atomic. So an individual string is not mutable. It's the case that it basically creates a new string in that case. But I'm not sure, because here I have a plus equal, and normally I wouldn't be able to do that with a mutable object. I'm not sure why lists are treated differently. That's a good question. So yeah, I think it's that when Python sees that empty string, it is treated like the same way as a 5 or something like that, where what's mutable here is def string, but an individual string isn't mutable. And I can prove that in the following, if that didn't make sense. In that I don't think I can do plus equals hello. Can try this. Let's see if this works. So that's because an actual string is a literal. So I can add things to a string variable, but it kind of creates a new object, but I can't do a plus equals on a string. Whereas if I try to do this, plus equals, well, this probably doesn't work either. I don't think this is a good explanation. Yeah, I'll have to come up with a good explanation for that. But you're right, that's a good question. And I'll update the textbook to kind of clarify more about what you should use and what you shouldn't use as default arguments. Lists are very dangerous. I can end up with that, and I'll find a more precise way of answering your question, Nico, and thank you for bringing that issue up. Okay. So for now, mostly you don't have to worry about that behavior. We can change our function miles driven to print a message which defaults to drive safely before returning the value. So here we have two default arguments, speed miles per hour and message. And then we're going to print the message and return hours driven times speed miles per hour. So we can have many defaults, as many as we want. So Python distinguishes it between the parameters without defaults, called positional parameters, and the parameters with defaults, called keyword parameters. All positional parameters are always required. So if it doesn't have that equal in there, you always need it no matter what. And the function will crash if not. All the keyword parameters are optional, and you can choose whether or not to specify them as arguments when you call them as functions. So if it doesn't have that little equal sign in there with some sort of default, it's always required. You need it. If it does have the equal, it's optional.
I have a question.
Yep.
What if, yes, you might thought these are all positional. What if you had, say you did not want to define, say there's 3 arguments. One is just a normal argument. One is the default value, and the second and the third one also has a default value. What would happen if you wanted to define the third one, but not the second?
That's a great question. So we will get, in 2 slides, we'll get to an example using exactly that. And there's 2 ways of handling that. Okay. So how does Python decide if you specify a bunch? This is what we need to understand the answer to your question. Which arguments to bind to which parameter? So first it goes through all the positional parameters because they're all required. So it goes through and chomps on those, assigns them the arguments to those parameters. If there aren't enough, then it's going to crash with a type error. Say, nope, sorry, not enough. It next goes through each keyword parameter and binds it to the arguments in order. Since keyword parameters are optional, this works as long as there aren't more keyword arguments specified than the total number of keyword parameters. So if I only have 3 more keyword parameters left, and Python has already gone through everything, and you specify 5 of them, it's going to be confused, and it will also throw a type error. So now we'll get to Nico's question. If you want to jump over the middle of the positional parameters, too bad, you can't, because all of them are required. So they have to be in order. With keyword parameters, which all have default values, you can pick and choose if you want to go out of order and skip over a keyword parameter. And to do that, you can specify the name of the parameter with the value of it as an assignment. Thus, if we wanted to call miles driven using the default speed miles per hour, but specifying new values for the parameters hours driven and message, we would need to specify that the second argument isn't speed miles per hour, but is message. And actually, the way that I code, and this is up to you, but the way that I code is just so that it's not confusing. Always with keyword parameters, I say what the keyword is in the equal sign. And always with positional parameters, you can't do anything else but say what they are. So when I use them as arguments with keyword arguments, I always say what it is in the equal sign. And that just makes it very clear for me what's going on. But that said, you can, and I have shown you that if you do everything in order, you don't necessarily need to have the message equal there if message was really the second keyword parameter. Okay, so a couple more things. Writing your own modules, we've done a lot with importing things, these modules. A module is just a file, a Python code file with functions, and it can be used as a module so long as the file is in a directory on your Python path. So say your file is called fancy_code.py, you could import it from another Python file or from the console with import, or from the IPython console with import fancy code from any other file. You can also import individual functions, so from fancy code import fancy function, or you can use from fancy code import star, just as you can with any other module.
What if you do not want to change your Python path and just want to specify it by path, for example, /fancy code?
So you can do that easily if the code is within a subdirectory of where your Python interpreter is run from. If not, the easiest way to do it is to add it to your Python path, but you can also, in your Python code, add things to your Python path. So one way to do that if you don't want to change your Python path from the bash console is to use the Python module to, before you do the import, add the full path to your Python path within the Python function. It's using the OS module, which I'll show you in a second, but basically you can, the OS module will let you do almost anything that you can do in bash from within Python.
Oh, like running programs.
Or like making directories. And there's also a sys module which can execute code and stuff like that. So I'll introduce just the names of those modules, but in the interest of time, I have a couple more things I wanted to say, just because the exercises this week are kind of cool, and they'll teach you these concepts better than I can just in talking. So I wanted to at least talk to you so that you've heard all this, have a reference for it, and this is all written out in the textbook too. So you can run a Python script from the console, the bash console, and it's very useful to be able to do that. When a file of code is intended to be run from the bash console, the file is often called a script. Since files consisting of Python code can be used as modules as well, we don't always want a big block of code to be executed automatically when we import a module. Python has a special way of indicating that code should be executed if it's run as a script. And this is with the statement if __name __ is equal to equals the string __main __ colon, and then followed by the code block to execute when the file is run as a script and not imported as a module. This is by convention at the end of the file so that it's easy to find and recognize. So basically, if I had a giant module of code, fancy code, and then I have this print hello world in this if statement at the end, if I do import fancy code, it's not going to print this. It's only if from the bash console I run python fancycode.py that it'll print this. So if there's stuff that you don't want to be run, if you import it as a module, say you're testing a bunch of things that take forever, if you put that in the main body of the file, every time you imported it elsewhere as a module, it would take forever to run because it's doing all this stuff.
So what is this __name __ variable? Where does it come What does it equal otherwise? If it's like, say, ran from Python script?
Yeah, so if it's a module, we can see what name is equal to. I don't actually know off the top of my head, but let's figure it out. Okay, so civil fancy code .py, and I'm gonna print name. Let's put parentheses around this. That makes sense. And then I'm going to do print name, print not a module. So let's see. So now I'm going to run from the bash console fancycode.py, and the name is equal to main everywhere, and it's not a module. Now I'm going to do IPython. I'm going to do import, or I'm going to do from fancy code import star, and now the name is set to the file's name. And because the file's name isn't equal to main, then that not a module isn't printed, so it's a module.
What if you change the name to main?
Oh, that's a weird one. Let's see. This is very evil, but we could probably do name equals.
Oh, that's even different. I was thinking of like changing the file name.
Yeah, this is a terrible idea, but let's try this. So now let's try Python fancy code, IPython from fancy code import star. So yeah, then it does change the name. So you can change that variable. So let's.
What if you do something else? What if you change the actual file name, like not?
Oh, I see. I get what you're saying. Yeah, then it'll change.
Well,
so.
if you change the file name to main, then.
Yeah. So yeah, it basically indicates whether it's being run by itself or not. And classes also have names. So a variety of different things have names that you can access. The only time we'll need to use this name, and usually the underscore things are things that you don't have to use very often. They're things that are used internally by Python, but it's for this script example.
What if you literally called the module, like what if you moved it to underscore name.py?
Oh, I see what you mean. There are ways of doing that. So you can, for example, do something where for a module you can change the underscore init__, which is what is run when the module is initialized, by creating a file that's called __init__.py in that same directory. So you can play around with calling modules that have those underscores. That's all advanced usage, so I'm not going to teach exactly how to do this, but it definitely is a case where if you have a question how it works, you can literally try it out from your Python console, just like I did, where I was like, I don't know exactly how that works off the top of my head. Let me code up a situation and see what happens. Or you can look it up. Yeah. But yeah, just in the interest of time, we have like 1 minute left, and I have one more thing I want to cover. So let's see, what do we have here? Default arguments, jumping over keyword parameters, running a Python script. Let's see. I'll do one more running a Python script from a console, and then we'll head out. Okay. So we just did this, and then you could also have arguments. So we can specify arguments to a Python script from the bash console by writing them in order as strings on the console. For example, we'd have what our hello.py file says be an argument to the script and call it in the following way from the bash console. And then, this will be our last slide, you can, from within hello.py, access the array of string arguments as specified on the console using the sys module. After importing the sys module in the Python file with import sys, the list of string arguments specified from the console is accessible via the sys.argv variable, and that's a list. So the first item in the list is going to be the name of the script, which in this case is hello.py. The rest of the items correspond to the rest of the arguments specified. In our example, just one. So,
wait, what does argv mean?
argv is a list of the arguments specified on
Why is
the
it
console.
argv?
Because that's what they named it. They could have named it anything else. So you can make your own module called nicosys that named it something else. But that's what they decided to name it. And I think it's because if you do any C programming, there's argc, there's a variety of different, so it has some history in terms of the name. But it could have, but it could have been called anything else. Here they chose to name it sys.argv. So there are a variety of different ways to specify arguments to a Python script from the console than just sys.argv. The argparse module is one example, but that's all I'll teach for now. So we'll take a 5-minute break, and these are all the concepts you need to address this week's problems.